OCR A-level physics. This is nuclear physics number 6, and it's the last one for nuclear physics. And what I'd like to do is talk a little bit more about one of these conservation laws, this idea of mass and energy. Okay, so look at this. I want to work out the amount of energy which is produced in this alpha decay. Okay, so you do this, calculate the mass defect, and then use that to calculate the energy released. Now, notice that we have to take into account a couple of electrons there, because the uranium-238, it's got 92 protons, so it's got 92 electrons as well. So the thorium will actually there will be 2 electrons produced as well. Yeah, conservation of charge. But work it out, 3, 2, 1, the answer is, okay, about 4.27 mega electron volts. The alpha particle doesn't get all of that because the thorium nucleus will actually recoil a little bit. The alpha particle will get most of it. And in this decay, all of the alpha particles have the same energy. Yes, all alpha particles will be emitted with the same amount of energy. Look at this beta decay and do a similar thing. Okay, now what we can do here is the electrons actually cancel if you figure it out here. So we're gaining a proton, but we're producing electron. So that's minus an electron, but there's the electron there. So in your calculation, you don't have to worry about them. Yeah? When you do your difference in mass on the left-hand side and the right-hand side. And then the neutrino has a tiny, tiny mass. You don't need to worry about that. And the energy released is about 0.155 mega electron volts. However, that's the maximum energy because now there are 3 particles, and when there are 3 particles you can't predict how much energy the beta will get because the neutrino is going to get some of it and the daughter nucleus will get some of it, and so you get a range of energies, and the missing energy actually led Wolfgang Pauli suggested that neutrinos existed. He suggested that there must be a 3rd particle getting some of this missing energy. There's a couple of more events we need to know about. I have mentioned this before, annihilation. If you get a particle and an antiparticle. So matter and antimatter cancel each other out, and their mass is converted into energy. You get 2 gamma photons emitted. Remember that the energy of a photon, E equals hf, and you might have to work out the minimum energy and or frequency of these photons. The minimum because the positron and the electron may have some kinetic energy, and that will go to your gamma photons as well. So there you go, looking if this mass is changed into energy using my little 931 shortcut, we get a total of 1.02 mega electron volts. So each gamma photon 0.51 mega electron volts each. That's the minimum energy, and then you can do E equals hf to get the frequency if they ask you to do that. And then I believe this is lastly creation, pair production. This is a gamma photon actually changes into a particle and an antiparticle. Usually it happens in the vicinity of another electron, so it doesn't happen in empty space. But in the vicinity of another electron, the gamma photon's energy creates this particle pair, yes, matter and antimatter. And basically the same calculation we did on the last slide, the gamma photon would need to have at least 1.02 mega electron volts of energy to be able to do this.